In today's class, we are going to learn about transport of oxygen in blood. Around 3% of oxygen is transported in dissolved form in plasma. Most of the oxygen is carried as a chemical compound, oxyhemoglobin. Hemoglobin is a chromoprotein. It is red in color and it has a weight of 68,000 daltons. There are 4 atoms of iron in ferrous form. So each atom is going to react with one molecule of oxygen. So 4 oxygen molecules will react with all the 4 atoms forming oxyhemoglobin. Look at the oxygen dissociation curve. Here the partial pressure of oxygen, as it increases, there is maximum saturation of oxygen and formation of oxyhemoglobin occurs. So this sigmoid curve or an S-shaped curve will have a left shift if the following factors occur. That is a decreased temperature, decreased 2,3-diphosphoglyceric acid, decreased hydrogen ion concentration. When all these factors increase, then the curve will shift to the right. The oxygen dissociation curve, when does it shift to the left? When the following factors occur. Let us discuss each here. Association of oxygen and hemoglobin forms oxyhemoglobin. So oxyhemoglobin, more and more oxygen reacting with hemoglobin, forming more and more oxyhemoglobin. So at that time the curve is going to shift to the left. So when does this occur? When there is a high partial pressure of oxygen. So if the partial pressure is very high, more and more oxygen is going to enter in. So basically this curve is going to depend on oxygen and carbon dioxide tension. So the partial pressure of CO2 has to be low. Yes, and why does it require a low hydrogen concentration? If the hydrogen ions are going to increase, then formation of hydrohemoglobin can occur. So that is why for the formation of oxyhemoglobin, a high pH or a decrease in acidity is required. Now coming to the temperature, if the temperature is going to be very high, then the body has to spend a lot of oxygen and energy, yes, to balance that temperature. So that is more and more oxygen will get consumed. So a low temperature is required in order to favor formation of oxyhemoglobin. Coming to 2,3-diphosphoglyceric acid, this compound has great affinity for hemoglobin. So once this goes and binds to hemoglobin, then it will cause a conformational change in hemoglobin, after which oxygen cannot go bind. So that is why there has to be a low concentration of 2,3-diphosphoglyceric acid. So let's say oxygen dissociation curve will shift to the right. That is, dissociation will occur if the partial pressure of oxygen is low. So when does it become low? When there is a high partial pressure of carbon dioxide, high hydrogen ion concentration or a low pH and increase in acidity. And the temperature has to be high with a higher concentration of diphosphoglyceric acid. All these factors are high except for oxygen. Whereas this will be the opposite if the dissociation curve is towards the left. But there are other factors also which are going to affect the oxygen dissociation curve. The first is carbon monoxide. The hemoglobin in our blood has 250 times more affinity for carbon monoxide than oxygen. So because of this, what happens is carbon monoxide will react with hemoglobin, forming carboxyhemoglobin, and because of which oxygen cannot bind to hemoglobin. When this happens, there is an oxygen deficiency that is caused in all the cells. After carboxyhemoglobin is formed, no more oxygen can bind to hemoglobin, because of which the person may die if oxygen deficiency continues for a longer period of time. Coming to fetal hemoglobin, if you look into the structure of fetal hemoglobin, it has 2 gamma chains and 2 alpha chains. Whereas in the case of adult hemoglobin, 2 alpha chains and 2 beta chains are present. So this gamma chain is going to give this fetal hemoglobin a greater affinity for oxygen. So the oxygen dissociation curve will be towards the left, that is, it is in favor of formation of oxyhemoglobin. Myoglobin, it has a single polypeptide chain, so it's a skeletal protein, and this also has more affinity for oxygen. But since it has only one polypeptide chain, it is going to bind to one atom of heme. Only one chain is there, isn't it? So that is why we are not going to get a sigmoid curve but a hyperbola. Coming to what is known as Haldane effect and Bohr effect. If you look at the level of alveoli, when more and more of oxygen is going to enter into the blood, it is going to replace more carbon dioxide from the venous blood. This effect is called Haldane effect. And what is Bohr effect? At the tissue level, when there is increased acidity or a lower pH, and when more and more of carbon dioxide is going to enter into the blood, then oxyhemoglobin will dissociate. Yes, so it is not in favor of, that is, this shows that the blood will have less affinity for oxygen. This is called Bohr effect. Now, what are our interpretations about the oxygen dissociation curve? When all the conditions are normal, we are going to get a S-shaped or a sigmoid curve. Even if the partial pressure of oxygen is 100 mm of mercury, the hemoglobin is never fully saturated. That means in that curve, we find that when the partial pressure of oxygen is around 95, the formation of oxyhemoglobin has reached 97% but not 100. So this means that it can never be fully saturated because there is always a level of CO2 which is present in our blood, and temperature is also yet another criteria for this. 2,3-diphosphoglyceric acid in the RBC, it has a high affinity for deoxygenated hemoglobin, and this will confer a change in the structure of hemoglobin, thereby preventing the formation of oxyhemoglobin. So this has to be low. And in the presence of weak or strong electrolytes, if you look at the curve, if it is going to be a strong electrolyte, then we get a sigmoid curve. Whereas if the electrolyte is weak, you are going to get a hyperbola. Now what is this P50? P50 is the value at which the partial pressure of oxygen will be in such a way that it causes 50% saturation of hemoglobin. So P50 value is directly proportional to 1 by affinity for oxygen or affinity of oxygen for blood. Yes, how much of oxygen is going to be present in blood at that time. So with this we come to an end of the today's class, oxygen dissociation curve. In the next class we look into how carbon dioxide is transported in the blood.